Good evening, everyone. Thank you for coming along and joining us on a sunny evening. Can you believe it? Seems a long time since winter, and of course the sun has been entertaining us a lot recently, directly and indirectly, but more than that shortly. So before we begin, there's a few announcements, a couple of things I would like to draw your attention to. First of all, we have rather a lot of telescopes in our observatory, not just the one in the dome, but a whole series of other telescopes that have been donated to us. If anyone would be interested in borrowing one of these telescopes and using it, I think we would much rather see that happening than it sitting locked away, not getting any attention. There's quite a lot of telescopes there. I can't describe them all just now. We've got a list of them. But if you are interested and you've got, get in touch with us. Come down here at the end of the lecture, or email us, or by whatever mode you prefer. Facebook, WhatsApp, we can do all of these things. Just let us know that you're interested, and then we'll look at loaning telescopes out to members of the Society. If we have guests here who are not yet members of the Society, welcome. You can join the Society, and then you get access to these things as well. Now, one thing we had a request for in the last session was beginning with imaging with telescopes. And so we're putting serious consideration into setting up a beginning imaging group in the beginning of the next winter in that session. But if there are other things that you feel we could be doing, let us know, tell us, because they're never going to happen if we don't know about them. And of course we need people who are willing to help out with these things. That's also always welcome as well. So next I want to hand over to David for some Secretary's announcements.
Thanks, Andrew. Hello everyone. There's just a couple of quick announcements, a couple of events happening. The first thing coming up is the Astronomical group. The next meeting of that is a week tonight, the 23rd of May. It's a Zoom meeting, 7:30 to 9 p.m. I don't know the subject yet, but it will probably, that Alec will be sent out and probably some further information.
So I know what it is because I'm giving the talk.
Oh, right.
It's about starting out, it's actually of interest at beginning imagers. It's about a small telescope that I bought recently and a mount and how to get started inexpensively with imaging. So that's the subject of the next imaging meeting.
Okay, thanks Andrew. And finally, just another event, the Observers Group, which takes place on Sunday the 9th of June,
Yep.
That's right. The subject, June 9th.
We'll be talking about the June night sky and whatever else is observable.
Again, that's via Zoom, 7:30 to 9 p.m. And that's all for now.
Okay. Thank you, David. So, tonight we are going to be treated with a talk which is very close to my own heart, and as any of you saw the Aurora recently will know, is at the heart of our solar system and responsible in part for the Aurora. Our speaker tonight is Dr. Alec Mackinnon. He is a seasoned solar physics researcher from the University of Glasgow. He's a senior lecturer there until he retired a few years ago. And he's worked around the world and on space missions. He's been in Paris, Berkeley, California, Sao Paulo in Brazil. He's got a Brazilian coming over to visit you. So he's still active even though he's retired in solar physics research. And really, there are not many people that have taught me more about solar physics than Alec has done. You'll also know Alec because for many years he ran the science content of the, sadly no longer with us, Department of Continuing Education, more affectionately known as DACE, which is a wonderful department at the University of Glasgow that trains so many of us astronomers here, and maybe some of us wouldn't have even met without that existing, let alone have benefited from all the knowledge. And it was really, in the last few decades, it was really Alec's diligent and passionate work that made that happen. And he's still going, even though the university doesn't pay him anymore directly. He's still active, and some of you might have seen him in Greenock at the weekend where he gave a talk at the BEA event there. So Alec has been my mentor academically, a good friend of mine. As I say, I've learned an incredible amount from him. And so it's my great pleasure to welcome him to give our talk tonight on the high energy sun. Please welcome Alec.
Can you hear me? Is the mic working?
Yeah, it's working, yes.
Thanks to Andrew for that lovely introduction. Oh, kind of up to it. As Andrew mentioned, the sun's gone mad the past few days. There seem to be X-class flares every few hours. They have all sorts of consequences. I'm sure many of you saw the aurora at the weekend. I didn't, because I was speaking early in the morning in Greenock on Saturday. I decided to go to bed before the sky really got dark. And then, of course, the next day we see all these pictures on social media. This evening, I'd like to talk about some of the same phenomena on the sun, which have those consequences on Earth, but rather than our immediate space environment here, I'll be talking about the phenomena on the sun themselves, and in particular about the highest energy aspects. So when we say high energy astrophysics is a thing. It's been a thing for decades. It's a phrase that people recognise, and it means something to them. So I don't know what you think of when you hear the words high energy astrophysics. Perhaps you think of supernova remnants. Perhaps you think of the explosive ends of the lives of massive stars and the shock waves that they throw out and the particles that get accelerated to enormous energies in those events. Or perhaps you think of active galaxies and the supermassive black holes at their cores and the jets of extremely energetic material that they throw out across hundreds of thousands of light years, emitting radiation across the electromagnetic spectrum. Or maybe you think of something like the famous supernova in 1987, which is still the supernova in the Large Magellanic Cloud. That's an image from Hubble and various other space missions showing how the blast wave from that event is banging into the gas between the stars that was lying around in its immediate environment, and very energetic things are still happening there. Or perhaps you even think of the very first few minutes after the origin of the universe, when all of the energy and matter in the whole of our universe was in such a condensed and high energy state that all sorts of things were going on that never happened in our cool, expanded universe nowadays, and we really have to turn to the understandings of particle physics to think at all about what was happening anywhere in the universe in those very earliest stages. Or perhaps you associate the words high energy with something quite different, with our attempts here on Earth to build devices to accelerate the subatomic particles to extremely high energies so as we can bang them into one another and see what comes out, like the famous Large Hadron Collider in CERN here. Whatever you think of, you probably think of something exotic, of extremes of scale, either very large or very small, and extremes of energy, rather than anything we might be interested to find in the solar system. So to see the words high energy put together with the word sun might be slightly surprising. That's an image of the sun earlier today, actually, from the NASA Solar Dynamics Observatory spacecraft. So that's probably pretty much what it looks like at the moment, with some nice sunspots. It's a fairly middle-of-the-road star. I remember when I was a boy reading books by Patrick Moore, for example, where he describes our sun as it seems very important to us, but it's actually just an average star. And I don't think that's quite fair to the sun. Its properties lie in the middle of the range of stellar properties. There are stars which are much bigger than it, hotter, more luminous, but the majority of stars are actually weirder and fainter and less massive and cooler. So it does lie in the middle of that range, but the stars that grossly outshine it are very, very few in number. Anyway, it's a fairly ordinary star. Its surface temperature is 5,800 kelvins, about 5,500 degrees centigrade. It's about 110 times the size of the Earth in radius or diameter, 10 times Jupiter, The smallest stars are a few percent of that, the biggest maybe 100 times. And of course its average distance from us is about 150 million kilometres. A large distance on human scales. 22.5 years travelling at passenger jet speed. But really in our back garden in cosmic terms. It's not obviously a high energy object compared to supernova remnants or neutron stars or supermassive black holes. Nonetheless, there is a high energy aspect to the Sun and to the things that we see happening in the Sun. So, when we talk about the high energy universe, we're probably talking about things we can study in gamma rays, the very shortest wavelength end of the electromagnetic spectrum. Let me say a word or two about what I mean, or two more about what I mean by gamma rays. So, I guess everybody in our room that this is familiar with the idea that light is a wave phenomenon. It's an electromagnetic wave. One of the numbers that characterises a wave is the distance between two crests or troughs of the wave, and we call that the wavelength. And our eyes are chemically sensitive to light with wavelengths in a certain range, from a little bit more than 700 nanometers to a little bit less than 400 nanometers. A nanometer is a millionth of a millimeter. In that wavelength range, our eyes respond to the light when it falls on them and we send a wee signal to our brains, and our brains interpret the wavelength of those waves as colour. Violet at the shortest wavelength end of that band, and red at the longest wavelengths. However, there is of course light of wavelengths shorter than 400 and greater than 700 nanometers. And the totality of all these different sorts of light we call the electromagnetic spectrum. The visible range is a very short part of it. Longer than red wavelengths, longer than the red end of the visible range, we have infrared. As we go to longer and longer infrared wavelengths, we come to what we call microwaves, which get used for radar and mobile phone communications, the shortest sort of radio wavelengths. And then longer than that again, we've got the radio wavelengths that we use for telecommunications, for radio, AM and FM and so on. Shorter than the visible range, we have ultraviolet that we should protect our skins from on hot days. And then going to shorter wavelengths again, we have what we recognise as X radiation. And then even shorter wavelengths than X-rays are what we call gamma radiation. There are some radioactive nuclei which naturally emit gamma rays, so they were discovered quite early on in the study of radiation and classed along with the alpha and the beta rays, as they were called at the time, which are quite different kinds of phenomena. The gamma rays are a form of light. As well as the wave aspect of light, we can also think of it simultaneously and paradoxically, the heart of the quantum world, as a stream of tiny particles. And the energy that each of these particles carries depends on where it sits in the spectrum, the wavelength or the frequency. So, in the radio wavelength range, for instance, meters, centimeters, nanometers, the energy of one of these particles, the photon, is so low that it doesn't really, the particle nature of that kind of radiation is not normally important. It doesn't cause transitions in atoms, it doesn't do very much. At the other extreme, in the ultraviolet and the X-rays and the gamma rays, individual photons carry so much energy that they can knock electrons out of atoms. So we know that we should hide from ultraviolet light. If you start to produce ions in places in your body that are not normally present, you allow all sorts of chemistry to start happening that wouldn't otherwise be happening, and you get those cancers and all the rest of it. So ionizing radiation, we know we should hide ourselves from. The visible light that our eyes are sensitive to, the average energy of a photon is 2 electron volts. If you've ever read the label of a Mars bar, you'll be used to energies in joules. A joule is a very large amount of energy by the standards of the world of particles and photons. So instead we use a unit called electron volt. The electron volt, the EV, the average energy of a photon of sunlight is about 2 EV. An electron volt, if you want to know, is 1.6 times 10 to the minus 19 joules. It's a tiny, tiny amount of energy. A few electron volts typically is enough to start knocking electrons out of atoms and making ions. And very many of the methods that we use to detect, even towards the business of making images, detecting those short wavelength forms of light rely on the fact that we can make ions with them. X-rays start at about 1,000 electron volts. Let me think. About 1,000th the wavelength of light, actually. And the gamma rays really start at something like 500,000 electron volts. So much shorter wavelengths again, much more energy in each of those individual photons. And the way that one of the technologies that we use to detect them looks like this. This is just a metal ring, but inside the metal ring there's stuff, so it looks like it's a crystal. It's very clear, so you can hardly see it's present. It's stuff called, there's various substances that is used in this particular picture here as a crystal of sodium iodide in it. Sodium iodide is what's called a scintillator. So when an X-ray photon or a gamma ray photon comes shooting into the crystal, it knocks lots of electrons out of atoms, and it's got enough energy that it knocks them out low down in the atoms, and then all the other electrons tumble down and they fill the gap that's been left, if you like, deep down in the atom. And when that happens, we get a wee flash of light, pretty much white light. And the nice thing about this is that the more energetic the photon is, the shorter the wavelength of the light, the brighter the flash. So you can use these for spectrum lines, you can use them to produce a spectrum in the X-ray or the gamma ray part of the spectrum. So this is a scintillator crystal. We might point a device at the sky. Maybe it's got a big shroud around it, so it only sees a wee bit of the sky at any one instant. We have a sensitive, a thing like a TV camera, but particularly sensitive, a photomultiplier tube. And it's looking at the crystal. Every time a photon, one particle of light comes into the crystal, it makes a wee flash of light. So the photomultiplier tube detects that, it sends it to some electronics. We could imagine doing the sort of thing we would do with a Geiger counter. We would have lots of e-clicks. And if our thing in the sky started emitting lots of X-rays or gamma rays, then the clicks would come more frequently. It would go like the old science fiction movies where you see where the alien spaceship is crashed in the Nevada desert and the scientists go and point their Geiger counter tubes. Same sort of idea. We could imagine scanning around the sky with one of these crystals and listening for where there were lots of clicks. And that would be some of it was bright in the X-ray cameras. I'm going to take a step back for a minute or two, actually. One of the major themes of 20th century astrophysics has been the exploration of the whole of the electromagnetic spectrum. Visible light, obviously, we can detect on the ground. We look at the sky and we see stars. Radio astronomy we can also do on the ground. The atmosphere doesn't keep, there's a great big band of radio wavelengths that arrive freely at the ground. So radio astronomy was the second sort of non-visible, well the first sort of non-visible astronomy to start being opened up from the 1920s. The other parts of the spectrum tell us other things, but in order to study them in detail we have to put on detectors above the atmosphere. So they're really products of the space age. very famously, if you have a cool thing that's just a couple of degrees above absolute zero, for instance, 2.7 degrees above absolute zero, then it mostly radiates in the microwave or even the radio part of the spectrum. And then if you look at things that are a wee bit hotter, you start to move to slightly longer wavelengths. If you look, we, in this room here, every one of us, you've probably seen in Glasgow Science Centre or somewhere else, an infrared camera where you point it at people and people all glow. We're a wee bit warmer than our surroundings. We and our surroundings all glow in infrared, and we stand out if we have infrared eyes. So at room temperature, things tend to glow in infrared. As you come to hotter things again, stars obviously glow in infrared if they're cooler than the sun and invisible light. And the hottest stars, actually, most of the light that they radiate is in ultraviolet. And then if we come to even hotter things again, things at hundreds of thousands or millions of degrees, we're talking now about the accretion disks surrounding black holes and so on, those things go in X-rays. And if we reach anything that's in the billion of degree range, then that will tend to go in gamma rays. So one way to think of this picture is from very cool things to very hot things. But that's not quite the only way of producing radiation in those parts of the spectrum. So we'll see. So the exploration of the electromagnetic spectrum has introduced all sorts of new phenomena to us. Black holes. Observational evidence for black holes is something that has come from X-ray astronomy and exploring that region of the spectrum. The winds of hot stars, a lot of the story of returning material to the interstellar medium, that's a result of ultraviolet astronomy. The studies in the cool regions where stars form in planetary systems, that's from infrared astronomy, and so on and so on. So we know that gamma ray astronomy is going to tell us about very energetic things and very hot things. That's how we produce those energetic penetrating certain radiations. There's been many space missions dedicated to it, but I wanted to mention this one particularly. This is the Hubble Space Telescope of gamma ray astronomy. It's called Fermi. On this slide it's called GLASS. That was its name after it, before it was launched. Gamma ray Large Area Space Telescope. So that tells you what it is. It's a gamma ray large area space telescope. But after launch it was renamed Fermi. For the famous Italian physicist, first man to make a nuclear reactor work, for instance, and contributed all sorts of fundamental ideas to nuclear physics and to astrophysics as well. So it's a very large spacecraft. As you can see, it's almost 3 meters high. It's powered by solar panels. It has two main instruments: the gamma ray burst monitor. I think they call it gamma ray now rather than GLASS. The gamma ray burst monitor, which is for monitoring gamma ray bursts and explosive events, things that go bang in gamma rays all of a sudden, and the Large Area Telescope, LART. The gamma ray burst monitor, the GBM instrument, has got several scintillator crystals, and each of them is pointed in a different direction. So each of them is looking at a big bit of the sky, but they're all seeing different bits of the sky in varying degrees. So if something is bright in this crystal, not quite so bright in its neighbour, much less bright in one point into the other hemisphere, we can start to localise those sources in the sky and say where they were. Those points that suddenly brighten up, produce gamma rays. The Large Area Telescope is a very different thing. It's not a telescope. It's not like any other telescope. It's the sort of device that works at these very extreme wavelengths where you can't make mirrors. They go through everything. They're even more penetrating than X-rays. Nonetheless, so what you do is you build a big tower. A gamma ray comes in the top of the tower and it passes through many sheets of tungsten. And as it passes through each of these sheets of tungsten, it's got so much energy, it can not only knock electrons out of atoms, it can actually lose some of its energy and create a pair of electron and positron. Oops. a matter-antimatter pair, as we see happening, for instance, in this cloud chamber photograph from the 1930s. So an energy photon, a gamma ray photon, has come in the side of the chamber here, and it produces two particles that leave tracks. There's a big strong magnet near the chamber, so if they're negatively charged, they curve that way. If they're positively charged, they curve that way. So the photon has lost some of its energy, it's moved to slightly longer wavelengths, and that energy has gone to creating two particles, an electron and its antimatter mirror image. So these things happen in many of the tungsten films down through the large area telescope here, and produces a signal in each of those regions as it goes down. So you get lots of signals, and you can reconstruct the energy that the photon had in the direction that it came from. So you don't make images as you do with a mirror or a lens, invisible light or ultraviolet or infrared or whatever, but you can tell where the photons come from, so you can start to build up a map of the sky. Yeah, sorry, this is the top view. So there's 4 by 4 towers, and from the side it looks like this. So your photon comes in at the top, and it makes particle-antiparticle pairs all the way down through here, and those things are detected and the locations are measured, and then you can do a sort of like billiard balls. The billiard ball goes into the pocket, and you know where the stationary one, where it was before it was hit. You can reconstruct where the white came from in the first place. Oh yeah. E equals mc squared. So the photon carries energy, it loses some of that energy, and according to this very famous relationship of Einstein's, that energy that's lost becomes things with mass. Here's a lovely picture of the Milky Way. I'm going to show one or two pictures which are they're oriented along the plane of the Milky Way. It's a mosaic, obviously a photo mosaic. It's from Digital Sky LLC.com. So in the centre of the picture here, we're looking towards the centre of the Milky Way, towards that direction that we know in the constellation of Sagittarius, and then there are lots of photographs which are joined up. So as we're looking in the centre of the Milky Way there, our way to Sagittarius, and we scan right around the sky through the plane of the Milky Way, and the two ends meet up 180 degrees to the end. If we're looking at things in the sky that flash, that turn on, and they're arranged around the plane of the Milky Way, then they're to do with stars. Things to do with stars. On the other hand, if we find them all through the sky, then they're not to do with our own local circumstances in the Milky Way, they're more to do with the galaxies and the universe on a cosmological scale. So here's a Fermi from the Large Area Telescope. Here's a map of the sky accumulated after 5 years of observations. And it shows you, first of all, a glow in gamma rays in the plane of the Milky Way. And it also shows you active galaxies. So galaxies that are bright in radio radiation, if we can make images of them, we might see a tiny, tiny compact core with jets, 1 or 2 jets of material squirting out of it. Galaxies with supermassive black holes at their cores, which material is falling onto, forming a big accretion disk, jets getting squirted out. In the accretion disk, the temperatures might get up to billions of degrees, so that's going to radiate in the gamma ray part of the spectrum, and the very, very energetic particles in the jets will also radiate in the gamma ray part of the spectrum, and we might be seeing both of those things in the gamma radiation from those galaxies. That's a famous one, M87, whose black hole was imaged famously. So we see two different sorts of things here. On the one hand, when we look at things that are extremely hot, the material in the vicinity of supermassive black holes, it's not, in a way it's not surprising to see it glowing in gamma radiation. But also, in the plane, all through the plane of the Milky Way, we're seeing bright glow in gamma radiation. And that's really for a slightly different reason. And it goes back to in our thinking, perhaps, it goes right back to the discovery of X-rays, to people experimenting with vacuum tubes. And so this is a little bit like an old TV tube. It's got an anode and a cathode, and we put a voltage drop across here, and we accelerate electrons from here, and they hit the front of the tube, which is fluorescent, and it glows. But if we've got some sort of obstruction here, then the particles coming out of the cathode, there's a shadow cast by the obstruction. It's telling us there's some sort of radiation, and it was really the study of the behaviour of gases in situations like this which started to open up ideas of atoms and ions and the structure of the atom, and together with radiation. For instance, this famous chap here, Mackinnon, he spotted that photographic film in the vicinity of one of these tubes was fogged, even though it was in a drawer away from the tube. This was the discovery of X-rays. The voltage in the tube here was high enough that the electrons banged into the front of the tube with enough energy to make X-rays. And if we give them even more energy, then they would make gamma rays. So this is the other way you can make gamma rays. You have some very, very energetic subatomic particles, and you have a target, and you bang the energetic particles into the target, and you'll get gamma radiation out. And that's what's happening in the plane of the galaxy. We'll see more in a minute about what those energetic particles are that are moving about in the plane of the galaxy and making galaxies. Here's another lovely example of the same thing. This is a picture. What does it look like? It looks like the moon. It looks like the moon with one side lit up by sunlight and the dark side. But all these funny wee dots through the picture, it's clearly not an ordinary picture of visible light. In fact, it's an image in X-rays from the ROSAT experiment, X-ray astronomy mission from about 1991. And the moon is bright in X-rays for the same reason. It's bright and visible light in X-rays. This is the side that faces the sun, but it's actually fluorescing because of ultraviolet light from the sun, and also because energetic particles in the solar wind are banging into its surface and making it glow in X-rays. This was actually one of the things people thought they might discover and they'd be able to detect when they put the very first ever X-ray detectors up in on balloons, actually, or rockets. You really throw them up above the atmosphere for about 5 minutes and then tumble back down, and we hope we'll see something interesting building up there. At the start of the 1960s. They didn't detect this, they found something much more exciting. They found binary star systems with black holes and neutron stars in them. But eventually, at the start of the 1990s, they did manage to detect the X-ray glow of the moon where it's been bombarded. In the same way, we might expect the moon to glow in X-rays, because the same energetic particles that are moving around in general in the plane of the Milky Way are going to bang into its surface. It's got very little magnetic field, it's got no atmosphere to protect it, it's just exposed in space. Energetic things can just bang into its surface. And sure enough, here is the moon. It's not really the moon. As far as Fermi's concerned, it's a point source. You're not going to go looking for the craters and things in galaxies. But here is the moon glowing much more brightly than the sky around it, as detected by Fermi. So this really underlines, if we've got a lump of stuff, doesn't really matter what kind of stuff it is, and we bang energetic particles into it, we'll make gamma rays. So maybe we can use that to study the energetic particles, maybe we can use it to study the thing that is being bumped into. Here's our 3-month movie of the sky as seen by Fermi. The bright spots are active galaxies, the blazars, or radio galaxies, very distant things again, supermassive black holes, jets of material. Some of those are highly variable, they vary rapidly. On timescales of weeks even, and you can see some of that. But the movie's repeated, I think, 3 times, and I'm going to start it again. So they just sit where they are and they brighten up and they fade away again. Some of them are more constant than others. But look down here. Did you see there? Look, there's something not terribly bright which you can see travelling across the image. What could that possibly be? It turns out this is half of the sky. It's got the galactic North Pole at the centre of it. So the galactic equator, the Milky Way equator, if you like, plane of the Milky Way is round the outside. Let's just show it one more time. And I should have said, again, an educated reading of this, I probably take too much for granted. The colours just represent how bright the X-rays are, the gamma rays are. Again there, did you see it? It got a little bit brighter, and you can see it travelling down. It's following the ecliptic, the plane of the solar system. The track around the sky, the sun follows in the course of the year, and it's the sun. It's the sun glowing faintly in gamma radiation, even though it's far too cool a star to do that. Again, like the moon, it's a blob of stuff. If we bang energetic particles into it, it'll glow. But it's a more complex kind of a target than the moon, because it's got strong magnetic fields and it's variable in some ways. But let's take a step back again and let's ask, what is being banged into those sources to glow? So the answer is cosmic rays. Cosmic rays is the phrase that refers to penetrating radiation which comes all the time from the cosmos, roughly evenly around the sky. They mostly because of changes in circumstances in the inner solar system. It was discovered really in 1910, 1911 by this Austrian physicist Victor Hess, who went up in a balloon to 5 kilometres, and what he discovered was that the level of radiation surrounding you falls off for the first kilometre as you come away from the ground, but then after that it starts to increase and it gets higher and higher and higher. It continues to increase up to passenger jet altitudes. And as a lot of folk know nowadays, I think if you take an hour flight for an hour or two at passenger jet altitudes, you get a wee dose of radiation, something like having an X-ray in Hess made these experiments following an earlier suggestion of the Scottish physicist C.T.R. Wilson, first Scotsman to win the Nobel Prize for Physics. Some of you might have heard my C.T.R. Wilson talk on other occasions. Oops. So these cosmic rays, as they were called historically, we might call them cosmic radiation, they are mostly individual atomic nuclei, ions, which have been given very high energies in some cosmic process. They move around in the plane of the galaxy, their directions change all the time because of the tangled magnetic fields through the plane of the galaxy, and they wind up arriving at Earth at the top of our atmosphere from all directions on the sky. At the top of the atmosphere, one of these very energetic particles will bang into a nucleus of oxygen or nitrogen, one of the gases that's present in our atmosphere, and it'll, again, some of the energy that this thing has when it arrives will get spat out as other particles. They'll bang into other nuclei, they'll produce more of this radiation, and we get a cascade of radiation that develops down through the atmosphere. Weaker by the time they reach ground level, but accounting for about 10% of the radiation that we experience in the background all the time. The rest, the other 90%, is tiny quantities of radioactive substances that are everywhere in the rocks, the our surroundings. These energetic particles, we're now pretty sure they come from things like the Crab Nebula. They come from the regions that are left behind when a massive star explodes as a supernova at the end of its life. So the supernova explosion shows out a blast wave. Any gas particles that encounter this blast wave, they bounce backwards and forwards across the shock wave, I should use the technical correct term. They bounce backwards and forwards across the shock wave and they gain more and more energy and they can get hyped up to very, very high energies. And then they leave the shock wave behind and start moving around in the plane of the galaxy and they wind up becoming the cosmic radiation. We reckon there's a supernova explosion somewhere in the Milky Way. Few times, the exact number isn't known because of course we can't see most of our own galaxy, it's shrouded by material in the foreground, but we reckon probably a few times a century, and that's enough to account for this radiation that arrives all the time from space. It doesn't quite arrive uninterrupted in the inner solar system. Here's a wee picture showing the sun and its surroundings. The sun and the gas that flows out from it all the time, the solar wind, moving through interstellar space. And the region called the heliopause, where the pressure of the solar wind falling off its distance finally equals the pressure of the gas in the Milky Way generally, and forms a sort of boundary to the region of the sun's influence, if you like, which the two Voyager spacecraft have now crossed. They're now in interstellar space. But depending on how the sun's behaving, on the sunspot cycle and so on, conditions out here will vary, and that has an influence on how much cosmic radiation can arrive in the inner heliosphere, in the inner part of the solar system. How do we study this cosmic radiation? Well, some of the studies, of course, nowadays are from spacecraft. But one of the nice ways that we study them is with the neutron monitor devices. There's a global network of these devices. I'll show you in a minute. But it's nice to remember this chap, Simpson, John Simpson. He was a project manager on the Manhattan Project. So he played a role in building the atom bomb. But he was one of the scientists who was dismayed by what he had done and by its implications for humanity. And he was one of the founders of the Bulletin of the Atomic Scientists, the organisation that each year decides whether to move the clock closer to or farther away from midnight. He wanted to use his nuclear physics knowledge for more peaceful purposes, and he started working on cosmic ray studies and space physics after World War II. He spent his career at the University of Chicago. So he was the instigator for setting up a global network of standardized devices called neutron monitors. Because the cosmic rays are charged particles, they arrive more or less easily at the top of the atmosphere, depending on how we meet Earth's magnetic field. So near the poles, they're travelling in along the magnetic field. And they can do that quite easily. Near the equator, they're having to cross the magnetic field, so they have to have much higher energies to do that. So if our detectors are spread in latitude, we learn about the proportions of these particles of different energies. And if we hope to detect sudden explosive events, it helps to have them a good coverage in longitude, because then there hopefully will be some part of the Earth where whatever explosive thing has happened is overhead for some of your neutron monitors. There is not one in Britain, but a chap called Fraser Baird, Glasgow physics graduate, has just finished his PhD, and he's shown that you can use devices used for studying groundwater for agricultural purposes. They're neutron detectors, but they're for a totally different purpose. But he's shown that you can detect the same sorts of things with those devices as you can with the dedicated neutron monitors, which is a very nice thing to have done. Here's a neutron monitor. Again, it doesn't look anything like a telescope. It's got great big things like the valves that we used to have in the old TVs and radios. They're filled stuff called boron trifluoride, BF3. Boron is great for detecting neutrons. When a neutron enters the tube and it meets a boron nucleus, then it sticks to the boron nucleus and makes a new nucleus that decays, gives you a wee click in your Geiger counter type device. The whole thing is shrouded in polyethylene, which screens out the lowest energy neutrons that are lying around everywhere that we're not interested in, because they're not sensitive to what's going on cosmically. And then the tubes are embedded in, it's about 6 tons of lead for a typical neutron monitor, a layer of lead. The lead also does a screening role, but it also acts as a sort of amplifier. So one neutron comes in and it causes a lead nucleus to split and spit out more neutrons, and they cause more neutrons to, they bump into more lead nuclei and spit out more neutrons and so on, and there's a bit of a cascade. So there's more neutrons flying around to be detected in your tubes. This one, as you see, is in Thailand, and it's quite high up. It's nice to have them high up. I would love to have one at Mackinnon. Not nearly as high as this, but it would be interesting to do. It's not going to happen.
No.
So these energetic particles, these cosmic rays, they're what are floating around everywhere, banging into anything that's present as a target, producing gamma rays. We can study them with the neutron monitors. We'll come back to the neutron monitors in a few minutes. First thing to mention is in that wee movie, we saw the sun moving around the sky and glowing rather faintly in gamma rays all the time as it did. Why does the sun glow faintly all the time in gamma rays? Because it's being bombarded by cosmic rays. But there's a couple of things that contribute to the gamma radiation that we see. One of them is cosmic rays hitting the solar atmosphere. But the sun, of course, has quite strong magnetic fields, and they make it harder for the cosmic rays to actually reach the solar surface at all. However, there's something else that goes on. It's called inverse Compton scattering. Compton was an American scientist. He was one of the leaders of the Manhattan Project, actually, a physicist. He demonstrated what's called the Compton effect in a Wilson cloud chamber, and he and Wilson shared the Nobel Prize in Physics in 1927. So what happens here is we have photons of visible light with an energy of, on average, 2 electron volts that stream away all the time from the sun, flowing out into space. A millionth of them arriving at Earth and driving everything that happens on our planet here. But every now and again, one of them will meet a very energetic electron, which is part of this cosmic radiation. So the photon is travelling along at the speed of light, but it doesn't have much energy. The electron is travelling along at very high speed, close to the speed of light. Two things collide. Afterwards, the electron has less energy, the photon has more. So it's got more energy, it's a shorter wavelength form of light. We can bang electrons up into the gamma ray part of the spectrum. So this is part of the reason that the sun glows in gamma rays. It also glows in gamma rays because the cosmic rays interact, they bang into particles in the sun's atmosphere. So some people thought about this some time ago, the early 1990s, and they imagined the cosmic rays coming in and making stronger and stronger magnetic fields and getting turned around again. And they had a sort of a cartoon of what the magnetic field looks like near the sun's surface, like this. And they made a calculation, and they estimated how much gamma rays we should see from the sun as a result of this happening. And interestingly enough, the Fermi observed 7 times as much gamma radiation as was predicted. It also depends on the solar cycle, but we'll come back to the solar cycle in a minute. And it comes mostly from low latitudes, near the sun's equator and the poles. None of that was really predicted. It's nice to look closely at the sun's outer atmosphere for this purpose. So here's a movie of the sun's photosphere, the visible surface of the sun near a sunspot, near one of the strong magnetic field regions. You can see the solar granulation. You can see the gas in the sun's outer layers bubbling. Cool gas rising up, hot gas rising up and cooling and falling back down again at the sides. And it's this gas moving all the time which determines the behaviour of the magnetic fields near the sun's surface. So, in fact, rather than this lovely cartoon that was used in those early calculations, it's going to look more like that. It's going to be a sort of spaghetti. Would I love to a nice dinner just before we talk. In the Italian restaurant, I had macaroni rather than spaghetti. I should have spaghetti, shouldn't I, for this talk? So the magnetic fields are all tangled up, and sometimes they come down and they don't keep going down. The particles fall in and will spend some time at the same sort of altitude, the same sort of conditions in the atmosphere. And it's a much messier situation than this simple cartoon. And I think it's maybe not that surprising when we find something a little bit different from what's predicted. Here's another gamma ray detector. This is the Hawk experiment, high altitude water Cherenkov experiment. Lots and lots and lots of big barrels filled with water. So very energetic gamma rays. It has to be at high altitude, and it's at 4,000 metres above sea level on the flanks of a volcano, Sierra Negra in Mexico, extinct volcano. So your very energetic gamma rays can penetrate our atmosphere at such high altitudes. They enter those tanks, they kick electrons to very high energies. The electrons make flashes of light because they're travelling faster than the speed of light in water when that happens, and you can detect the gamma rays and tell what direction they're coming from by looking closely at all these wee flashes of light. And this has actually detected even higher energy gamma rays from the sun. Let's have a wee look now at solar activity. How am I doing time-wise? I should stop now, should I?
No, I think it's 8:20 seconds.
Just to remind you of things I'm sure you all know, here's a wee movie showing sunspot groups getting carried round by the sun's rotation. The weird groups appearing and disappearing again. See the date changing at the bottom, date and time. The weirdest groups persisting for a few hours, a day or two. The biggest groups getting carried across for a week, a couple of weeks, occasionally even going around the far side of the sun for a fortnight and reappearing again. Not moving around, but appearing at locations that change gradually during over the years. As is well known, the number of these spots goes up and down on a roughly 11-year cycle. And this is showing how the number of sunspots takes about 5 years to climb up to maximum and 6 to fall away again. And then you start to see new spots appear, and 5 years to the next maximum, roughly, and 6 to fall away again. And it's been doing this for, well, it's been doing this quite steadily since the start of the 18th century. And we're heading for sunspot maximum again, probably later this year or early next. We'll see how it plays out. The sunspots are just the most visible apparition of the sun's magnetic fields. The sun's strong magnetic fields, which permeate and structure and are responsible for the existence of the outer atmosphere. And the nice way to study the sun's outer atmosphere is in ultraviolet light, because it's at temperatures of hundreds of thousands or 1 or 2 million degrees, so it glows mostly in ultraviolet light. We've got ultraviolet cameras and telescopes in orbit, and we produce these beautiful images showing that it's dominated by these loop structures with magnetic north at one end and magnetic south at the other end. The sort of field lines that you drew with iron filings in the science class at school, but in a gas which is ionized. All of its constituents are electrically charged. These magnetic field lines take on the character of structures.
charged ions and electrons can travel easily along the magnetic field, but really hardly at all across it. And looking at the ultraviolet emission from the sun gives us another picture, a different way of looking at this 11-year cycle. The corona glowing more faintly at minimum and brightening up, becoming highly structured with lots of highly heated, brightly glowing ultraviolet emitting regions at maximum, and then falling away again to the next minimum. We mentioned the importance of the very far outer reaches of the solar system for the cosmic radiation arriving in the sun's vicinity. And that's really underlined by this. Sorry, it's a slightly complicated graph. It's got year along the bottom, 1960, 1965, sorry, 1950, 55, 60, 65, 70, 75, and so on, up to about 2000 here. The yellow curve is the sunspot number, and roughly the number of spots on the sun, how spotty it is, how many strong magnetic field regions there are, how much strong magnetic field area there is on the surface. And the blue curve is the counts in neutron numbers. So that's telling us how much cosmic radiation is arriving at Earth. And we see that when the sun is spottiest, the cosmic radiation is lowest. When the sun is quiet, the cosmic radiation is at its highest. And that's really underlining how the sun's magnetic activity modulates the arrival of this cosmic radiation at Earth. A wee movie, the sun's bright disk hidden in the middle here, that's that circle, and it's showing, look at the date passing quickly at the bottom here. We're seeing these so-called coronal mass ejections, expulsions of magnetized gas from the sun, which happen maybe several times a day when the sun is most active. So when a coronal mass ejection arrives at Earth, the magnetic field combines with Earth's magnetic field, it helps to shield the whole of the planet from cosmic radiation, and we can see the cosmic rays go down significantly. Currents in neutron numbers. So the sun's magnetic activity modulates cosmic radiation arriving at Earth, but it also contributes to it, and events at the sun can also produce energetic ions which will bang into the sun's surface, use it as a target if you like, and produce gamma radiation. And that happens in the events of solar flares. This is a very, very famous event, the very first solar flare observed by two Englishmen, Carrington and Hodgson. Carrington was making a drawing of a sunspot group and he saw two patches brighten up on the 1st of September 1859. They brightened up until they looked as bright as the star Sirius would appear normally in his telescope. And then they faded away again over the next 5 minutes or so. It's quite a nice picture of what we would nowadays call a two-ribbon flare. And this is the famous event that was followed by spectacular displays of the aurora, which terrified folk near the equator and woke people up in the middle of the night that were camping in the southern states of the USA. Would have had technologically significant consequences if it was to happen. So that was the first ever observation of a solar flare. We now know that these things happen a lot. Small flares happen all the time. Maybe the small flares are mostly responsible for heating the sun's outermost atmosphere. That's not quite an answered question yet. But solar flares are frequent events. The solar surface in one of these, they're explosive events. The solar surface brightens up for a few minutes. There's emission across the spectrum from radio waves to X-rays and occasionally even gamma rays. So here is a picture of the sky as seen by the Fermi mission in March the 6th, 2012, and here is the sky as seen by the Fermi mission on March the 7th, 2012. And And there's a great big bright thing. The brightest thing in the gamma ray sky is the sun. I'm working at the moment with a wee group of colleagues in various countries. One of them is a scientist from Pisa in Italy who didn't know very much about the sun. She was working on Fermi and cosmic gamma ray astronomy, and this really grabbed her attention. That all of a sudden the sun might become the brightest thing in the gamma ray sky. So she's been working ever since on solar flares and gamma radiation. Here's a movie in ultraviolet light of the occurrence of a flare on the 10th of September 2017. So look how a great big region of the sun brightens up, gets heated explosively, glows in ultraviolet light for tens of minutes. You can see the loops, material in the loops heated. Actually what happens is the material, the flip points, the ends of the loops gets heated so much that it's not in pressure balance anymore, it expands into the loops and it sits there and it glows brightly as it cools down and starts to fall back down again. And of course, the magnetic things that drove the flare in the first place are continuing to happen. The loops are expanding gradually, or maybe some of them are falling back down. It's a very dramatic event. Now this is ultraviolet light, so it's gas of tens of thousands of degrees really. But this particular event produced radiation right across the spectrum, right into the gamma ray part of the spectrum. And it also produced energetic particles that could be measured on Earth. So here's a graph. It's a graph of time through September, from the 1st of September here to the 1st of October here. And there are several things you can see in the graph. There's a steady rate of counts in the neutron monitor. And that's just the general galactic cosmic ray goings on that's happening all the time. And then there's a couple of sudden drops in here. Those are called Ford-Bush decreases. And that's the coronal mass ejection arriving at Earth and protecting us from the cosmic radiation. And then here, on 10th of September, at the same time as that solar flare, there's a sudden increase in the radiation. And that's energetic particles that have been accelerated in association with the flare arriving at Earth and causing a cascade of radiation through the atmosphere and being detectable even at ground level. Another wee movie. It's an alternative way of the sun's just out of sight off the edge of the picture here. And you can see all sorts of things here actually. You can see it's a sort of, it's called a difference movie. Successive images are subtracted from one another. So something that's moved into the image is bright, something that has moved away from it is dark. You can see the waves that travel away from the sun all the time in the solar wind. Let's watch it again. That bright thing there is Earth. The spacecraft is a long way from the Earth. It's moving in the plane of the solar system. It's a coronal mass ejection and it arrives out at Earth. That particular one caused displays of the lower when it arrived. But it would also protect us from cosmic radiation. So, here now from several different neutron monitors. These two are at the South Pole. This is from Oulu in Finland. This is Newark in the USA. That one's Northern Canada, I think. No, it's not. I'm not sure. I'm sorry. I'm not sure where that one is. It's quite low latitude. I'll need to check. Anyway, all of the cosmic rays can arrive at the South Pole, but as you come to lower and lower latitudes, a smaller and smaller proportion, you need to have a higher and higher energy to be able to count in the neutron monitor as you come to lower latitudes. So by the time you reach this one here, there are none of the cosmic rays from the sun that had enough energy to cause a signal in this one. So we're learning about the range of energies produced in the event as well. Some of these energetic particles travel away from the sun and arrive at Earth, but some of them maybe travel backwards and hit the solar surface, so they need gamma radiation. Horrible boring graph, sorry. The red points are gamma rays from the sun. look at the scale along here. It's not minutes or hours, it's date. 10th September, 11th September, 12th September. What I should have is some people sitting under the sun, and we would pretend they had gamma ray eyes, and the sun would suddenly brighten up in gamma rays, and they would sit there, and they would read a book, and they would have lunch and drink a glass of wine, and watch the TV, and the sun would move across the sky, and it would keep glowing. So the events of this, most of the events of the solar flare last tens of minutes, at most. But viewed in gamma rays, this thing keeps going for hours and hours and hours. And that's a big question in solar astronomy at the moment. Why does it keep going for so long after the events of the flare? And most of us believe that the answer is to be found away out in interplanetary space. That the particles are accelerating in a shock wave in front of the CME, and some of them make their way back to the sun. But this thing, the stuff out here keeps happening, even though it's a long way from the sun. And some of the particles can make their way back and continue to produce radiation. Maybe that's what's happening. It's still being debated. I think we'll finish with this one. This is lower energies than fairly large. What we're going to see here is we're going to zoom in on that sunspot at the edge of the sun there. Red is low energy X-rays, blue is higher energy X-rays, purple is gamma rays. This is from a satellite called RESI, which could make images in X and gamma rays. So the blue image, the blue spots were where the electrons are travelling along the magnetic field and hit the solar surface. They hit it at a target again, at the front of the old vacuum tubes, and they make it glow in X-rays, and they heat the atmosphere at the same time. Let's watch that game. The purple is where ions hit the atmosphere and do something similar. But it's really, really interesting in this famous flare from 2002 that it looks as though the electrons, the blue patches that have gone now, and the ions, the purple patch, hit different parts of the atmosphere. So that's letting us look very, very closely now, trying to understand the details of what's going on in the flare. We'll just skip. No, actually, I'm going to stop. I will stop and I will end with my favourite movie here from the flare of 25th of February 2014. Also a very bright gamma ray event. Just intense spikes in gamma radiation. We're viewing it here in ultraviolet light again, and we see some nice loops. They're sitting there, they change very gradually, and all of a sudden a current takes off, goes to large value one of them, makes the magnetic field lines twist and throws the whole thing off into interplanetary space and produces some disruption in the magnetic field that's accompanied by strong electric fields and turbulence and good shock waves and goodness knows what all. It results in those energetic particles that make gamma radiation. So, to conclude, there is certainly a high energy aspect to the things that happen in the sun. Some of it's local to the sun, brief in the explosive events of solar flares, but the other part of it comes from the fact that the sun is sitting there and it's a big blobby lump of stuff that can be used as a target, and there is this cosmic radiation which is found everywhere in plane and Milky Way. It's a niche thing, high energy solar physics. Very exciting, but not too many people working on it. I think it's exciting, I hope you agree. Thanks for listening.
Well, thank you very much, Alec. Have we got any questions for Alec about the high energy sun? Jim?
Was there a massive sunspot in 1816?
Yes.
That had no sun.
Oh, 1816.
Yeah.
I don't know. I think attempts to find a connection between sunspots and weather events on Earth have not been very successful.
I think that was a tiny event.
The Some boiler erupted in 1815, and that was the ash. But you could see through the ash of the sun, barely, and people killed themselves because they were scared. But I've read that, but I'm never convinced that it was so big. As I said,
Okay, you can't see a sunspot with the naked eye. Be very careful. You have to be looking through something that blocks out the light. But the large sunspots.
Volcanic ash?
Volcanic ash. I wouldn't do it personally. I wouldn't go around looking for volcanoes and standing next to them, hoping for them to erupt so I could look at the sun. But in principle, you can see a sunspot with the naked eye.
I'm told last week's sunspot folks saw with the naked eye. The big one that gave us the big
There was a naked eye one there. Just is there not a correlation with very bad extreme winters with solar minimum? So there's things like the Maunder minimum, which lasted about 75 years. There was no sunspot activities, so you would, I'm trying to remember when that would have been, it was in the late 18th, early 19th century, if I remember that one right.
It was from about the 1645.
Oh, earlier than that, right? And what would happen is that the River Thames would freeze and they would have ice fairs. And then you've got things like 1947, which is a really bad winter. Then you had 1963, which was an extremely bad winter. And then we had 1982. And then more recently, it was at there was one that, what was the date that one? 2009. 2009, which I think they said was the coldest winter in Scotland since the 1680s, and it happened when the sun was at minimum. And I seem to remember that the sun took a wee bit longer to come out of that minimum then than what they were expecting. So there was a book published by one of the TV weather guys, I can't remember which one it was, and meteorologist, and he reckoned there may be some kind of correlation with sunspot activity in the weather.
A lot of papers have been written on that subject, and have been written on things I've spoken about this evening.
Mm-hmm.
It's quite hard to find a convincing correlation, I think. So you mentioned the Maunder minimum and the cold winters of the Maunder minimum. There were terrible climatic conditions, I think, across northern Europe. But it seems that it was only northern Europe, it wasn't global.
Mm.
When there's a big sunspot, over the cycle, the sun, the brightness of the sun, if you like, the amount of radiation that the sun emits varies at the 10th of a percent level. So that's a very small variation, actually. That's not enough to account for big changes in climate from one year to the next. So if there really are such changes, then you need to look to some other mechanism. But then, why would you look for that other mechanism if you're not quite convinced that there is something there at all? The most convincing correlation I know of between solar activity and Earth's climate is called the Van Loon-Lubitsch effect. And it's in the temperature measured above the polar regions. And it seems to anti-correlate with the sunspot number, if I remember correctly, but not all the time. So there's a circulation of wind in the equatorial regions, which is called the quasi-biennial oscillation. So it's half the time, one year it's blowing east-west, and the next year it's blowing west-east. And if you look at the sunspot numbers and temperatures, only in years when it's blowing eastward, when it's blowing with the sense of the Earth's rotation, then you get this effect. So if you look at every second year, you get this correlation. But if you look at the years when the winds are not blowing in the other sense, there's no correlation, they're unconnected. So that's a really subtle thing. That's not going to have a great big effect immediately without a whole lot of other non-linear effects that are being understood on on the climate generally.
What do you think is the cause of the 11-year cycle? Do you have any theory yourself? Or any preferred theory?
Well, again, there's folk that work in that in much more detail than me. In general terms, there's two mechanisms there's two ways that the sun produces stronger magnetic fields, concentrates, regenerates them. One of them comes from the fact that the sun it's a globe of gas, it's not a thing like football, so it doesn't all rotate at the same rate. Near the equator, the gas goes around once every 25 days. Near the poles, it's more like 35 days. So if you imagine a magnetic field line that's stretched out along a line of latitude, the bit near the equator is going to run away, and that's going to take some of the magnetic field that starts out north-south, and it's going to convert it into east-west. And there is something similar that happens because of the convection, the bubbling of the gas rising up and falling back down again, that takes east-west magnetic field and converts it to north-south. So the interplay of these and the effect that the magnetic fields have back on the gas can produce a sort of a cycle. Accounting for the 11 years in detail is a much more messy and detailed job. And I think the picture, as I understand, the picture that I just sketched has been revised in a fairly big way in the last 10 or so years to include an important role for events at the very base of what's called the convection zone, the outer third of the sun, where the gas is actually moving, bubbling convection.
A lot of detection techniques you presented are traditional experimental nuclear physics ones. So I was wondering if there is any people working explaining the phenomena you presented from a nuclear astrophysics perspective.
Yeah, absolutely. I didn't go into any detail on that, but in order to understand, are you a nuclear physicist?
A nuclear one, yes.
Do you use any of the big Monte Carlo codes, Geont and Fluga?
Yeah, I used to.
You use Fluga?
No,
Geont. Use Geont. Well, we use Geont as well.
Okay.
The trick is well, there's a few things that need to be thought about. Nobody has incorporated plasma turbulence and its effect in continually randomising the directions of the ions in Geont. I worked with these other colleagues on at least including magnetic fields in a way that's accomplished. It doesn't take years for your code to run. So yes, exactly. And we use those codes because of the knowledge of the rates that an energetic ion will produce pions, which will decay into gamma rays and so on. All those things are quite well understood and already included in those big codes. So yeah, we lean very heavily on laboratory nuclear physics knowledge to interpret these things.
One of my favourite telescopes, the Chandra X-ray telescope. Absolutely love it. And they're not going to replace it. What's interesting is the tube you showed, the boron scintillating.
No, it's not a scintillator. It's not a scintillator. It's like a Geiger counter tube. So your gas is sitting there, a neutron enters the tube. It is captured by a nucleus of boron, but once you add this extra neutron to the boron nucleus, it's an unstable isotope and it immediately decays. It spits out what's called an alpha particle. The alpha particle knocks electrons out of atoms and it allows a little pulse of current in the tube. So you get a click, like the Geiger counters, but the clicks are triggered almost entirely by neutrons. So it's a neutron counter. It really is a counter.
So the Chandra telescope is like one cone inside another cone.
Yeah.
And the X-rays are gathering in that way. I can't quite believe it. I've not looked at the details of what scintillating materials we got. I've got it in my mind. Thanks.
Okay, well, if there are no more questions, we just thank Alec once again for the And that wraps up our lecture programme for this session. We will be back at the end of the summer with more, but we're not completely inactive over the summer. We will be doing solar observing out at Mugdock at the observatory when it's clear and when people are free. And so we'll send messages out to members to let you know when they will be, but they'll be spontaneous, you know, when the weather permits. And hopefully that'll be more days than it's been this winter, which has been terrible.
I'll continue to do a monthly thing about what's in the night sky, because astronomy and space doesn't stop just because it's a star.
That's true. Okay, thank you very much, everyone.